Okay, welcome everyone. I'm happy to introduce Mykola Shpot from Lviv, Ukraine, who is going to tell us today about boundary conformal field theory, in particular about layer susceptibility. Please, Mykola.
Thank you, Slava. I am honored and happy to do this talk, and I am very grateful to Slava and to organizer for for giving me such opportunity. In fact, the history of this work is rather long and a bit strange. In 1995, when I was in Germany and worked with Hans Werner Diel, there appeared a Condmat preprint of Makevity and Osborne, where they somewhere in the text introduced the integral transform, which they identified as a Radon transform, and wrote down the transformation which goes in both directions. At the same time appeared another paper by Makevity, and this one remained without any consequences until recently. It wasn't cited at all, and the method which was proposed there in these two papers was not applied anywhere. And I started these calculations in 1995, just after the appearance of this preprint, because Hans Werner proposed me to look at this. He has studied this paper with care. And when I decided to publish things in 2019, I contacted Hugh Osborne, and he told me that I should consult the paper by Leander Rastelli and Van Rees. I knew about this, but I didn't realize that it's so important for me. And so I learned about the bootstrap which occurs in this situation, and I shall use things which were proposed in this paper. But first of all, I shall do an introduction about the critical phenomena in a semi-infinite system to give a physical background. We shall be concerned with semi-infinite space and with transitions which occur there at the bulk critical temperature. When you go from the high temperature disordered phase to the ordered phase, and the interactions at the surface are not strong enough to order the surface as itself, then occurs the ordinary transition, and the order at the surface is induced by the presence of the critical bulk. And if the surface interactions are so strong that the surface can order independently at the same time as the bulk at the critical temperature, then we have special transition. But when the interactions at the surface are even stronger, then it is possible that in the absence of any field, any ordering field in the system, the surface orders spontaneously, and then if you lower the temperature in the presence of the ordered surface, you encounter the extraordinary transition. This extraordinary transition will exist at a zero surface field when it is possible that the surface is ordered. This means that the condition for occurring the extraordinary transition is d equals or greater than 3. However, in 1977, Bray and Moore argued that the same situation will happen when the surface field H1 orders the surface instead of temperature. And in fact, the asymptotic behaviors of both situations are the same, but this corresponds to different physical situations. This situation with non-zero ordering field at the surface is normal for critical absorption, and that's why it was called normal by Michael Fisher and Hans Werner Diehl. And in order to exist, this transition must occur in the half-infinite bulk of the system. And this means it will be already present for d equals 2 and more. And quite recently, there were new papers by Metlitsky and Paris and Toldin, where they say that in two-dimensional surface, when the order parameter equals to n, number of order parameter components is equal to 1, it can occur the Kosterlitz-Taulis transition, and then after this comes extraordinary transition. So the situation will be different, as I discussed before at this phase diagram. And also Paris and Toldin already in this year argues that also with n equals to 3, one has to reconsider this phase diagram. We will be interested, first of all, in the extraordinary transition, and I shall present some explicit results for it, and now a bit of history. The name and the transition were proposed for the first time in the paper of Lubensky and Rubin in 1975. And there they calculated the mean field correlation function. And this result for the correlation function, for the two-point function, remained a single one up to our work with Parijat Day and Tobias Hansen. On the basis of scaling considerations of Bray-Moore and also of 1 over n results, large n results of Monod and Takabe, they concluded that that critical exponents of parallel correlations and perpendicular correlations are given just by d plus 2 and this combination for longitudinal components, and eta parallel is equal just to d, the number of space dimensions, for the transverse components. This eta parallel and eta perpendicular are related to the scaling dimensions of operators. So eta, which is here, this is Fisher exponent, it enters scaling dimension of field, and the anomalous dimensions is eta half. And the scaling dimension of the leading boundary operator is connected with eta parallel through this relation. Well, the next important development of the theory in this context was done in conformal bootstrap by Leander Rostelli and Van Reyes, and also there were other people who worked here, Gliozzi, Liendo, Maineri, Raga, and so on. And also I have to say that it is not only a theoretical construction. The extraordinary transition can be seen at the experiments. And the main type of experiments is adsorption experiments. Critical adsorption occurs in semi-infinite two-component systems when one of the components is preferred by the surface. Our geometric setup is here. We are considering the half space R plus D in D dimensions, and the boundary is flat and located at z equals to 1. In the bulk of the system, leave the fields, which are blue, and at the surface we have boundary fields, which are red and have also heads. And boundary conditions are imposed on the surface, and depending on boundary conditions, we will have different kinds of transitions in semi-infinite space. Here we have to do with operators which are defined in the bulk and at the boundary. This can be very different operators, and they can also mix when they have equal classical dimensions. One of the important representatives of surface operators is the ZZ component of the stress tensors, tensors which live on the surface. In terms of the field theoretic approach,
can I ask a question?
Yes.
If you go back 2 slides, there was something I was a bit confused about. So in this, the leading boundary operator, the scaling dimension, you have this eta parallel.
Yes.
And this looks like the anomalous dimension of this operator. But then if I look above this eta parallel, it's either d or d plus 2. I mean, I would expect it to be something, I mean, if I have some O1 symmetry or something, I would expect it to be something that depends on this n.
Cancel n.
Yeah, I mean, I'm just wondering, like this eta parallel, is that d or d plus 2?
When we have, in this case, eta parallel, okay, is this one. This eta parallel equals d plus 2 is related to the stress tensor, which has the dimension d. And when you substitute this d plus 2 here, you will reproduce delta head equals to d.
Ah, I see. Okay, I see. So then the leading boundary operator is the stress energy tensor.
Yes.
Okay.
Yes.
Okay, I see.
Mm-hmm.
Yes.
Now we go to the force theory, and the Landau-Ginzburg-Wilson-Hamiltonian looks like this. It has the simple, the usual phi to force term, and well, in the bulk, the only difference is that the integration over that goes from 0, not from minus infinity. And otherwise, we have the surface term here. And well, it describes the phenomena which I discussed before, that at the surface one has some different situations than in the bulk. And boundary conditions look like this. And depending on the boundary conditions, we have different transitions. The field is n component, and I have supposed that the field on the surface goes along the first component of the field. So it is the longitudinal component, and other components with n equals from 2 to n, I equals from 2 to n are transfers. This longitudinal component phi 1 of z is non-zero. It is non-zero above the critical temperature, at the critical temperature, and below. So we have to take in account it all the way. And it is called also the order parameter profile. And when the transition is ordinary or special or surface, then this profile is 0. And only at the extraordinary transition, it does not vanish. And that's why it's most interesting case. And this transition, according to the picture of the, which I showed before, occurs when h equals to 1, h1 equals to 1, and arbitrary surface interactions, arbitrary surface enhancement, or And this is extraordinary transition. And critical adsorption corresponds to the case when H1 is non-zero, and then for arbitrary surface enhancements, you will have the same kind of transition, which is now called normal. Two-point correlation functions.
Are these two things, Miko, are these two things completely equivalent or not equivalent?
They are not completely equivalent. Asymptotically, they are. The critical, the leading asymptotic exponents and such kind of behaviors are the same, but corrections to scaling are different, amplitudes and different, and so on. And,
but example, for example, for the current of the ON current, for the conserved current of this theory, I was wondering if the symmetry breaks spontaneously, then the current should still be conserved even on the boundary, while if the symmetry is broken explicitly, then the current may not be conserved on the boundary, although it is conserved still in the bulk. Is this playing any role in the theory of this? Could this be used to distinguish these two cases? Because whether the current is conserved on the boundary or not, it seems to be an important.
Fairly speaking, when we did these calculations, we used H1, non-vanishing field. So in fact, this corresponds to the second situation that you say, normal transition. And in fact, one works in this case already at the fixed point, and I wouldn't be sure how to take into account the another situation when the surface was ordered spontaneously. I don't know. But the difference which you described can be, yes, I agree. But I wouldn't know how to take it into account.
Okay.
In this situation, at the present stage for us, important is that the correlation function of two bulks of two fields in the bulk away from the surface are given by the scaling function, which depends on one variable, which can be identified as a cross ratio, and another power. And this correlation function can be written in several different forms, depending on which variables you prefer. And more subtle things concerning the conformal invariance on the surface, which were, for example, considered in the paper of Nakayama, we in principle don't care about this. The main thing is here, and Xi is the most standard and most frequently used variable in the scaling function. It is the ratio of the squared distance between 2 points and for ZZ prime. In fact, the same function can be written in this form, where the parameterization is a bit different. And here appears another cross ratio V squared, which I find also a good variable, not only Xi. And one can see that the situation in a semi-infinite system is similar to the 4-point situation, because here really play the role 4 points. X and Y and X prime are in the bulk of the system, and X hat and X prime hat are their mirrors with respect to the surface. So if you introduce the standard cross ratios U and V, as in the lecture of Viti, Then you can see that the ratio Xi is given simply by U4 standard, and this V squared is the ratio of U over V. So in principle, we have to do with the same cross ratios here.
I don't understand, but is V4 conformally invariant?
V4 is standard variable in the bulk theory when you have 4 points. But if you can use it also in the boundary conformal theory, and it is invariant.
So V, you are saying that V is also a conformally invariant quantity.
Green over red. Yes. Yes. Yes, it was also used in older papers, and it appeared in such papers like Ono and Tokabe and Gomper-Wagner. They calculated simply things, not in principle from the large and expansion, not on the basis of the conformal field theory. And they found already such variables. They are also okay.
I'm just confused. So there has to be a formula for V in terms of psi then.
Yeah, it's about psi over 1 plus psi.
Ah, okay. This explains it.
Yes.
Thank you.
Yes, I have written this here. Okay, so we have important asymptotic limits which are crucial here. In the large distance limit, bulk limit, when the distance between the points is much less than the distance from the surface, and they go away like this. This is the bulk limit, and in this limit we reproduce the bulk as a standard bulk behavior, which is given by this power. And the same situation, psi goes to 0, appears when you look at the short distance behavior of the points when they come together in the bulk. And the opposite limit, psi to infinity, it is relevant to the specific surface quantities. It is relevant for correlation exponents, which I discussed before, at a parallel, at a perpendicular. So when r goes to infinity and z's are fixed, if the points move away in the planes parallel to the surface, then this behavior is governed by the power of r, which is given here, and involves eta parallel, the exponent of parallel correlations. If z prime goes to infinity and the other conditions are fixed, you have to deal with parallel perpendicular correlations with corresponding critical exponent. And then the same situation with psi goes to infinity appears when one of the points goes to the boundary. And this is the short distance limit, which corresponds to the boundary operator expansion. And this is in fact the short distance singularity of the correlation functions near the boundary. Now comes the thing which you know very well. In the paper of McEvity and Osborne, they introduced the conformal blocks, which are essentially the Gauss 2f1 functions. And they were formulated for the operator product expansion when the points touch in the bulk, and the boundary operator expansion when you can expand an operator close to the boundary in terms of the operators which are sitting on the boundary near this operator. They are violet. And the big thing that has been done in the paper of Leander, Rastelli, and Van Rees was that they summed up these conformal blocks which were introduced in the paper of McCavity and Osborne, and made them coincide. Yes, they equated these expansions and introduced the bootstrap equation, in fact, for these different kind of expansions. And again, in the same paper as I showed you before, comes up the Radon transformation. McCavity and Osborne says that you can integrate the two-point function over directions parallel to the plane. And then you obtain another physical quantity, which is called layer susceptibility, chi of z prime. It depends only on positions of z and z prime, and the parallel directions are integrated out. And it is the same that you will take the pz representation of the correlation function, where p is the parallel component of the momentum, set p to 0, then you will have the same. And the important point is that this integrating the parallel directions gives us the Radon transform R of rho, where rho is defined here. And it is invertible. So if you can have somehow this function, this means if you calculate the layer susceptibility, you can reproduce the correlation function, the scaling function g of xi for the two-point function. Simple examples are very simple. When you look at the Dirichlet propagator, which is the difference of the bulk propagator minus the same thing between the point and the mirror image of the other, you will have a simple scaling function g of xi, blue. And in the statistical mechanics, they normally used this pz representation, which I don't like too much. And if you take the limit p to 0 in this pz representation, you simply obtain that chi of z and z prime is the minimal value of z and z prime. If z is less than z prime, it's simply z. But if you write the same thing now in the scaling form, you obtain the usual power, which should be, it is power from here, and the scaling function, which is simply 1/2 zeta 1 square root of zeta. And this zeta is the ratio of minimal z and maximal z, z to z prime in the situation which I consider all the time. And now you have to go from the variable zeta to the variable rho, apply the inverse Radon transformation, and this reproduces the blue function which was above. So just a very simple way, you obtain the usual correlation function for the Dirichlet propagator, scaling function for the Dirichlet propagator. A bit more involved is exercise with extraordinary transition. The pz representation could be seen in the paper of Eisenriegler. And when you take the limit p to 0 in this expression, you obtain the layer susceptibility for the extraordinary transition, which is somewhat more complicated. This is the power zeta to 5/2. And now the same procedure, inverse Radon transformation, produces this scaling function, which was already found by Lubensky and Rubin in their first paper on this matter, and then successfully reproduced several times in 4 dimensions. In 4 dimensions, you see here appears the logarithm of psi. And because already in the mean field level, we have 4 minus d somewhere. This pole in epsilon cancels and comes up the logarithm in 4 dimensions. Now comes the observation which we have done with Tobias Hansen and Parijat Day. If we simply take the inverse Radon transform of any power of zeta, then you will get as a result the boundary block in terms of psi. And there is one correspondence. You can also do this in the inverse direction. You can Radon transform the boundary block and obtain the power of zeta in the layer susceptibility. And this tells us that we can, in fact, calculate the layer susceptibility, expand it in powers of zeta, and then simply with a transformation of this kind, reproduce the boundary operator expansion for the correlation function, which is here left. And in fact, here we have to do with a bit enhanced representation of the scaling form for the layer susceptibility, because in fact, I have splitted here the main behavior in the boundary limit, which is given by delta hat leading non-vanishing operator in boundary operator expansion, times the function y of zeta, which is regular when zeta goes to 0. And in fact, it adds to the leading behavior just a Taylor expansion. So if we can try to write the same form for the correlation function, and my guess would be that if we extract the leading behavior in the bulk limit, the leading behavior in the boundary limit, then we remain with the function f tilde, which will be regular in both situations when v goes to 0 and v goes to 1. And now comes again a simple example of the Radon transformation in a simple situation. When we have the function j of xi as a simple power of xi plus 1, we can define the variable rho as always, and we know its relation to the variable zeta, and the Radon transformation for such, simply for such function, when we accept that xi is of this form, gives us the expression in terms of rho. Then we have to go to the representation in terms of zeta, expand in powers of zeta, and then use the observations which we have done and obtain the boundary operator expansion for this simple function. And this principle, which was used here, will be further employed in the case of more complicated extraordinary transition. So in this case, we have to calculate the layer susceptibility. Its calculation is relatively simple because this is a calculation of a correlation function at the 0 external momentum. So these diagrams can be calculated with some care, and then we obtain two layer susceptibilities, the longitudinal and transverse one, which are just of the same scaling form, which I showed you before. This is a scaling form with extracted leading singular behavior at in the boundary limit zeta to 0. And this function and the functions which appear, these explicit functions, they are very symmetric. And if you got something which was not symmetric, you should look for the errors and you would find them. So here, in fact, in this form, the logarithm of zeta, which was present here, is exponentiated in order to have this form. And still logarithms remain which depend on 1 minus zeta, which corresponds to the OPE limit, to the bulk limit when 2 points come together, that and z prime, this ratio goes to 1, and logarithm of h plus zeta plus 1, which will be the contact non-analyticity when the point and its mirror come together. And anyway, we can expand this function y of z, or the content of square brackets here, and obtain the expansions in terms of powers of zeta. And we succeeded to determine the coefficients which appear in such expansions. They are explicit, they are given explicitly here. And so it was for the both cases of longitudinal and transverse layer susceptibilities. In this way, we obtained, in fact, the boundary conformal field theory data for the layer susceptibility in terms of leading boundary operator scaling dimensions and expansion coefficients. In fact, the leading operator for the longitudinal component was the stress tensor at the surface, and it has a fixed value d as a scaling dimension. And also we had the contributions of even powers, even terms in the sum, infinite tower, which went further. And similarly, in the case of transverse components, we had a situation with leading with the scaling dimensions of the leading operator d minus 1. And this should be the analog of the displacement operator for the broken rotation current, as explained as Markov. And so we have this way all the data for the two-point function after the transformation via Radon transform. So we transformed the powers of zeta in the scaling form of the layer susceptibility, and knowing the coefficients which appear, we now know all the coefficients and scaling dimensions for the correlation function. And it is possible to sum up the resulting sums and obtain the explicit results. The correlation function was found in the form of the epsilon expansion, where the value of the scaling function g at d equals to 4 is here in blue for longitudinal components and green for transverse ones. And the contribution of order epsilon is given here. It's a bit complicated. And this was known before, and this was not known. And the distance between the first result and the second is many years, between 1995 and 2018. And it can be seen that they have a correct OPE limit and boundary expansion limit. Everything is okay here in this explicit expressions. And now we can use the boundary, we can use the bootstrap equations, equation which was introduced by Leander, Rastelli, and Van Rees in the form which is up here. So we have to use here not the connected two-point function, which was discussed all the time before, but the full affine function. It means that it is a scalar product of two phi's, and also it has to include the disconnected part, the product of two one-point functions here. And we had to calculate this one-point function explicitly in order to be consistent. And so we have calculated this mu naught squared and added all other correlation functions, and the result was compared with function which is predicted by the bootstrap equation, which is which will give us some information on the bulk spectrum. In fact, we take this form and rewrite it slightly with some coefficients and so on, and write formal epsilon expansions for this function f OPE, so that it must contain the epsilon -1 term and finite term and O of epsilon terms. And in the same way, we formally expand the scaling dimensions and operator product expansion coefficients. These formal epsilon expansions are a bit involved, and the point is that they contain the derivatives of blocks with respect to epsilon, which has to be taken at epsilon 0. And they contain logs and logs squared. And this should be, in fact, compared with the explicit result to draw some conclusions. And the way in which we have done it was a comparison of discontinuities of these both functions. The discontinuities here were considered in the interval from minus of psi from -1 to 0, where the Gauss function is analytic. And so it was possible to define, to determine the bulk CFT data. We have determined the coefficients, the expansion coefficients. And in fact, these are the coefficients which are some averages over possible operators, because there can be different operators which have the same classical dimension, which can mix, and then we are not able to disentangle them, and we find, in fact, some averages of contributions of such operators. And these are the results for the coefficients. And these are the results for the scaling dimensions. So the general scaling dimension is delta K is given here. This is the value in 4 dimensions, and the remaining part corresponds to the deviation of all 4 dimensions. Gamma K in the first order of epsilon is well known. And we reproduce it, and then come other gammas at the level of second order of epsilon expansion. This is also standard, and this is already something different. Anyway, when K equals to 0, we have to do with the energy operator. This is phi squared. And in this way, we reproduce the known epsilon expansion to the second order for this scaling dimension. And this is given by d minus the eigenvalue of the renormalization group for the temperature, which is 1 over nu. Delta 1 is connected to the exponent of the scaling correction to scaling. This is related to the presence of phi to fourth terms to the Cartan constant of the phi to the fourth term, and gives the exponent omega. And this is the standard delta phi which was used in this calculation. And our results agree with known exponent or known scaling dimensions which were derived before. These are of Derkachov and Manashev, which are the dimensions of phi squared to the power k plus 1. And we have, in fact, also the agreement with large n expansion in the overlapping region when we expand over 1 over n expansions to the second order of epsilon. And this these expansions agree at the level of 0k, 0, 1, and 2, which correspond to the 5 squared, 5, 4, and 5, 6. And then they deviate. And this means that further occurs some mixing of operators. And further, we cannot say which kind of operators are contributing here. And after this main part, I would like to say some words about possible implications. In principle, up to now, only one has considered the bootstrap equation for the correlation function. But here we had to deal with Relayer susceptibility, which is a simple physical object, simple to calculate, and which is simply related through Radon transformation to the two-point function. And if we expand it simply in the powers of zeta, we can apply the known relation to boundary operator expansion and reproduce the correlation function. So it would be interesting to do the same to another side of the same relation. We could consider another limit of the same layer susceptibility. Here was the limit of this. It was here the surface limit, and in the opposite limit, the bulk limit, zeta to 1. It would be interesting to construct another expansion of the same layer susceptibility, which would also contain all information about operator block expansion, I mean coefficients and scaling dimensions. And this expansion can have such form. It can be simply another power expansion, and it would be interesting to learn somehow how to do it and to formulate the bootstrap equation not in terms of comparison of Gauss or series of Gauss power functions, but comparison of simple power series expansions. And I tried to use the variable y, which is symmetric with respect to z and z prime, and which goes to 0 when zeta goes to 1. That is in the bulk limit. And in fact, I have seen the non-analyticity related to the energy operator of the bulk operator expansion, but it has not still done systematically. I don't know how to produce the infinite series and how to produce the relation between such expansion and OPE. in the way similar to this relation. And I would find that it is an interesting open problem. And also, I think that it would be not without interest to look at the layer susceptibility simply for ordinary transition. This correlation function was calculated several times. In fact, Dietrich in 1981 calculated the second order of the correlation function at the ordinary transition in this form, which had still to be Fourier transformed to obtain coordinate representation, and they didn't do it. Another attempt to calculate the same function was by Ono and Tokabe, and they also produced some expression which was not very good tractable. And finally, in 2018, Bisse, Hansen, and Söderberg have calculated the next order, not the next, the O of epsilon squared order, which was simple and transparent, and which also was in agreement with the scaling form proposed by Lubinsky and Rubin in their first paper. If you look at this form and take here lambda 0, you will see that you will reproduce xi at this place and xi plus 1 at this place, and it is just the same form, but these people have done it up to epsilon squared, and this was proposed on the basis of the first order calculation. And I would say that it can be interesting to calculate the layer susceptibility in this simple case of ordinary transition and look what happens. And this would be, I think, the simplest calculation of this correlation function to this second order, because the calculation of Bisse, Hansen, Söderberg, it was a rather involved calculation. And I think also that if it should be possible to calculate the layer susceptibility to the next order, to the third order of in epsilon, and this would be this would give new exponents, because the exponents for the ordinary and special transitions, they are also known only to epsilon squared, and this is so the situation holds from these old years, from 1981. Nobody has calculated more, and I think that using layer susceptibility, it should be doable. And finally, there can be several extensions to different models and different functions, and already just in the recent publications, there were some applications of this kind in Herzog Kobayashi and Gimenez-Grau and others. And there is also another thing which I wanted to tell you. I noticed that people say about some Youngian bootstrap for massive Feynman diagrams. In fact, they don't do bootstrap, but they write differential equations based on the Youngian symmetry for massive Feynman diagrams, solve these equations, and then produce results for massive Feynman integrals. And my observation was that, in fact, the Feynman integrals of this kind with the masses M1 and M2, they are the same as the inner integrals when you calculate layer susceptibility or correlation function in the boundary conformal field theory. If you change P to R to the parallel direction, parallel components, parallel coordinates, and masses to Z's. In fact, they say, these people who calculate Feynman integrals, that they use this kind of Youngian transformation which is in fact the same as the conformal transformation introduced by Cardy, which preserves the surface because they treat masses like extra coordinates, and it is the same as you treat masses and z coordinates in the semi-infinite system. So there is a clear analogy between this Youngian symmetry, which they discussed, and the constrained conformal symmetry in the semi-infinite systems. And for example, the integral which has single powers of propagators here down, they are expressed in terms of the Appel function, where the second argument is just v squared, which we discussed before, when we make this replacement, masses to coordinates. And this is the conformal variable. And since the integral is not conformal, it depends also on a scaling variable, which is here. And when we go to the situation when the conformal symmetry holds, this is the d-dimensional integral with single propagators. We will obtain just the same scaling form which was encountered all the time before. Here is the bulk behavior, so to say, and this is the scaling function f of v squared, where v squared is here. And it is the same which appears in this situation. And I wonder whether some more analogies can be done, and whether it can be possible to use simple Radon transformation in this situation, because if you calculate a Feynman integral at zero momentum, it's much easier as to do the same integral for non-zero external momentum. So you can in principle calculate conformally invariant integral at zero momentum, then do a Radon transformation and reproduce it in the coordinate representation, something like this. So, and also the Youngian symmetry, I didn't hear this name in this conference, but I think it is also some topic for the people which are here. And at this stage, I shall stop and thank you for your listening.
Okay, thanks, Nicola.
Thank you, Akra. Thank you.
You're welcome.
Let's see, are there any questions? I don't see any raised hands, but maybe people should just speak.
Yeah, I have a question. I probably already answered this. So if you take two fields phi to the boundary, and you have directly boundary conditions, and we know how to do this. We just put the mirror charges. So does this also hold in the interacting theory? Yes, it's equivalent to saying that it's conformally invariant. No?
You mean whether the pictures with mirrors is okay for the interacting theories?
Yes.
Yes, yes. Mm-hmm.
It has to be like this because otherwise it would not be conformally invariant.
So, sorry, but I don't know if that is completely true. I think, so I mean, in 4 dimensions, or this 4 minus epsilon dimensions, then it's, you have like this image symmetry or this mirror symmetry up to order epsilon square at least. But for example, if you will look in 6 dimensions, 6 minus epsilon dimensions, and you have like a phi cube interactions in the bulk, this theory is non-unitary, and then you don't have this mirror symmetry at order epsilon.
Mm-hmm.
So there's some, I mean, I don't know when you have this mirror symmetry, but it doesn't seem to, I mean, it's not general. Or actually, I think you have it when you have it depends on the operators exchanged in the boundary channel. So usually it's like normal derivatives, and if you only have even or odd normal derivatives, then I think you have this mirror symmetry. But if you have mixed, which is generally the case, then I think it's broken.
Mm-hmm.
So you can basically see this mirror symmetry from the conformal blocks as well. And you see that each boundary conformal block change up to a phase. And if they all have the same phase, so either even or odd or normal derivatives, then you have some mirror symmetry.
Mm-hmm.
So if you look at 5.4,
Okay, thank you.
I mean,
Yes.
so this reflection symmetric configuration, so this also proves that it's unitary on the boundary?
I don't know. This is an open question, I think.
Yeah, usually people always like asking these questions whether there is mirror symmetry in boundary CFTs, but I think for interacting theories, there is no reason to expect why it should be there, because yeah, mirror symmetry is just a consequence of linear equations of motion and free theories. So there was a question from Bertrand.
I mean, Slava, if you say it's conformally invariant, then you don't have much space for changes, no? Because it has to be the cross ratio, and the cross ratio is.
It's naive to think that you can construct a correlation function of a boundary CFT by just doing mirror transformation and borrowing a correlation function in the usual CFT in full space. That's just not going to work, because there's much more than can go on the boundary that you cannot model in such a simple way. So in free theory, you know that the correlation function in the boundary CFT in half space satisfies some linear equation, and the correlation function in full space that also satisfies some linear equation. So provided that the boundary conditions are satisfied, these things should agree. That's why the method of images works in free theories. But in interacting theory, this doesn't satisfy any simple differential equation. So you cannot just specify boundary conditions. So that's why there is no reason that the correlation function in the boundary CFT should agree with any correlation function in the bulk CFT appropriately mirrored. So there was a question.
The idea would be that the 2-point function in the bulk, sorry, the 4-point function in the bulk has to be related to the 2-point function with the boundaries.
It's not going to be related. That's the point. Because there's a boundary in the middle, and it just changes things dramatically.
So Mykola, you try to calculate this?
I don't know. I simply had the impression that if I look at this picture and these variables, I can exchange these points with heads and without heads, rather arbitrary, and I shall remain with the same function. That's why I suppose that this symmetry holds.
Yeah, actually, I'm not
Okay.
sure. There's kinematics. We should distinguish kinematics and relations between the actual physical 4-point functions and physical theories.
Okay, it's only impression.
Can I ask a,
Tulip, it works, okay. No?
There was Bertrand Duplantier first, but he lowered his hand. Bertrand, do you still have a question?
Yes.
Please go
Use-
ahead.
Hello. Yeah. Hi, Mykola. Thank you
Hello.
for the talk. I just have a naive question. Your results seem to make perfect sense when n equals 0. And so number of components going to 0. So what does it physically correspond to in terms of polymers?
I suppose it should be a critical adsorption of polymers. Naively, too.
Hmm.
Why not?
Normally, that's a special transition, right?
I don't know. Critical adsorption, cannot it be for polymers at the ordinary?
No,
I'm
as
not
I-
expert here.
Yeah, no, it's a naive question. I don't remember all the details, but at the moment,
I am not expert, but I suppose that this extraordinary transition, normal transition, exists for this case, and one discusses polymers in the situation of critical adsorption, but I'm not sure. I guess on.
Mhm. No, because analytically they seem to make perfect sense.
Perhaps.
You did get finite results.
Mhm.
So can I ask a rather naive question? If you take the ON theory in 4 minus epsilon dimensions, can you characterize the different transitions just in terms of the spectrum of operators in the corresponding boundary conformal field theory? I mean, are these clearly the only possibilities, forgetting about anything to do with boundary conditions and so on, but just in terms of the spectrum of boundary operators?
Well, for different transitions, we shall have different spectra. Leading operators are different, and the spectra will be different, and then this will be.
But is there some
different
way of
situations.
saying that these are uniquely selected for a specific theory, the ON theory? I mean, without
I suppose
you have a set of conformal field theory axioms for the bulk theory, and then you want to join on a boundary theory, but you don't talk about boundary conditions.
Yes, I suppose, but that the simplest case would be the ordinary transition when you have the leading operator as the normal derivative of the field, and then some spectrum above. And this should work, I think. It would be not so easy for the special, but I think ordinary, it is the case. If I correctly understood the question.
But Hugh, is your question is why do we always talk just about this ordinary, special, extraordinary? Why we expect that there should be actually many other boundary conditions?
Yeah, that's basically it. I mean, could there be other potential boundary theories which you could join on in some non-trivial way?
Yeah, I think there should be, because we can take this boundary CFT, which I mean, let's just take, for example, this ordinary transition. So ordinary transition has some operators. So we can try to couple this ordinary transition CFT to some purely local CFT living on the boundary, and arrange some RG flow, which will flow to some other CFT on the boundary.
Yeah, I guess that's true, but you
Excuse me? You are muted, Hugh.
you don't want two decoupled theories. I mean, I
They will be
suppose
initially decoupled, but now we couple them. This should be possible at least for the ordinary transition, because for the ordinary transition has this phi hat operator, which is relevant. And so we can, let's take another CFT, which will have some other relevant operator, let's call it chi. It's just on the boundary. And so we couple these two CFTs with the operator phi hat times chi. And now we start flowing. So we might flow somewhere.
And well, we don't know where that would go.
So we could pick some, yeah. So if such a if for example this operator chi has some appropriately dimension such that phi hat times chi is weakly relevant, then maybe we will reach still another boundary condition. Which might not be experimentally realized because in an experimental situation this field chi might not be necessarily at our disposal. But for example, the extraordinary condition, it has no relevant scalar operators, right? Is this correct? Nicola, does it have any relevant scalar operators, the extraordinary transition?
No.
So in that case, we cannot play such a game.
So does the ordinary flow to the extraordinary on the boundary? Well, no, probably not. But,
They can be connected through the surface field, and they are very close. In fact, when you take into account the surface field, when you consider this, then you can even think of extraordinary transition as some kind of ordinary in the presence of H, something like this. They are similar somehow.
I thought that the RG flow was kind of different. You can flow from special either to the ordinary or to the extraordinary, depending on the sign of the coupling that you add in the special. But how do you flow from ordinary? I mean, if you start flowing from ordinary, you will not flow to extraordinary. You have to somehow, not continuously, because you have to somehow go through the special.
Mm-hmm. I don't know, because you can simply switch the field.
I don't know. It was wrong. Sorry, I was wrong. So indeed, if you take ordinary and if you turn on the operator phi hat with some coefficient, then you will flow to the extraordinary because this is going to be breaking the symmetry.
Yes.
Yeah. But that's the coupling which breaks the Z2 invariance. But if we have this, the example that I had in mind is to take some other CFT. Okay, in your case, there was no Z2, it was a ON invariance. If we take some other CFT which also has ON invariance. Yeah. Any other question?
So when you compute your two-point correlation function for a half space at the extraordinary transition, in your recent paper, you see that it turns out to be a sum of correlation functions for respectively Dirichlet and Neumann boundary conditions in lower dimensions. Is this something that just happens to be the case for the half space? Or is it something maybe a bit more general that you can say that you can generally obtain correlation for the extraordinary transition by summing correlation for the other possible boundary conditions in Dirichlet and Neumann?
I wouldn't say so. In principle, what I described and what can be seen here, indeed, you have here the Dirichlet propagator in d dimensions. It is simple as the Neumann propagator in d minus 2 dimensions, but it is not the Neumann propagator in d minus 2 dimensions because the variable xi, it is related to the vectors in d dimensions.
Yeah,
So
yeah.
d minus 2 is only a nice game to play. It looks like this, and this is nice. It's good for calculations, but I wouldn't say that it can have any physical implications.
Okay, got it. Thank you.
Okay, well, there are no further questions, then I'm going to stop the recording. And we thank again Mykola for this nice review of boundary critical phenomena.
Okay, I thank you too, once again.